Hello friends, this is Vimal. Today's discussion we will start with AC with capacitor. So, a capacitor is connected along an alternating source as shown in the diagram. Let's see with the capacitor and the voltage drop across it is taken as VC. So, that is the part I am drawing it. So, here the first equation remains constant. So, V is equal to Vm sin omega t is the expression. So, the voltage expression doesn't change, it remains same. But here, since we are using a capacitor, we'll be using the capacitor's equation. So, by Kirchhoff's law, we'll be using the Kirchhoff's loop rule. That is, V minus Q by C is equal to 0. So, that is the expression we are going to see here. So, from this, we can take it as Q is equal to CV. That is the capacitor equation. Q is proportional to V. So, Q is equal to CV. Therefore, V is equal to Q by C. So, that is the expression I am going to take over. And also, we have the expression I is equal to rate of flow of charge. That is I is equal to dq by dt. That is current is equal to dq by dt. So, I am using the expression, therefore, I is equal to d by dt of this particular Q expression. So, Q is equal to CV. That is expression. We are going to use it. C into V. So, I wrote it. The next step, I is equal to d by dt of C, I keep it as it is. Instead of V, I take it as Vm sin omega t. So, just I am writing the expression. So, here we are going to differentiate it. So, here the differentiation. So, C and Vm is constant. I take it outside. C into Vm. So, it is d by dt of sin omega t. So, a normal simple differential method we are going to use it. So, C into Vm. When you are differentiating it, it becomes cos omega t. And once again, when differentiating omega t, you will get it as omega. So, omega C Vm cos omega t will be the expression. So, it is Vm by 1 by omega C. So, just I am going to use the relation. I am going to explain why I am writing like this. So, Vm by 1 by omega C into cos omega t can be written as sin of omega t plus pi by 2. So, in the previous video, I have explained about this. So, I am just making it. So, in the previous expression, we have done it. So, it is V by 1 by omega c sin omega t plus pi by 2. So, then we are using the Ohm's law. I is equal to V by R, which is nothing but V by 1 by omega c. So, on that 1 by omega c, I take it as Xc. So, it is taken as Xc. Where Xc we call it as capacitive reactance. So, we call it as Xc is equal to capacitive reactance. So, Xc is equal to 1 by omega c is the expression. Now, in the same format for AC, what will happen? So, when you are connecting an AC circuit, what will happen to the capacitor? When you are connecting the same capacitor in a DC, what will happen? So, what happens to the frequency? So, that is the part I am going to take it next. Therefore, Xc is equal to capacitive reactance. Therefore, for AC and DC, I am separating it up. So, for AC, then for DC. So, here AC the frequency will be 1, 2, 3. For DC the frequency will be 0. So, as we can see here, Xc is equal to 1 by omega c, 2 pi nu c. So, when I take nu is equal to 1, what will be the condition? 1 by 2 pi. When I take nu is equal to 2, it is 1 by 4 pi. So, when you see here, as the frequency increases, the capacitive value decreases. The capacitive reactance decreases. But in the case of an DC current, it is 1 by 0. So, we take it as the capacitive reactance becomes infinity. That means capacitor offers infinite resistance for DC to pass through. So this could be the example why an fan cannot run under DC current. Yeah, so a ceiling fan can run only under an alternating current. So that is the example. So if it is asked in the exam, you can just clarify it. So a capacitor, a ceiling fan cannot run in AC. So a ceiling fan can run only in AC, not in DC. That can be explained here. So why a fan cannot run in, can run only in DC can be the, this could be the answer. So why a fan cannot run in DC. So since the value is infinity, the capacitor offers infinite resistance for DC current. So a fan cannot run in DC. So that is what we are going. Next will be the phasor diagram. So as I told you, the phasor diagram has to be drawn only from the graph. So the first part we will be taking it as the graph itself. So first you have to draw the graph, then only you have to go for the phasor. So if you keep this rule as constant, you won't commit errors. So the next part is the phasor. So please be careful when you are drawing it. Therefore, I am drawing the phasor, the same waveform. First I am drawing the waveform. So the voltage curve remains the same. There is no change in it. So there is no change. Whereas the change starts from the alternate, that is the current. So here we can tell that the voltage is lagging the current by 5/2. So that is the reason. So you can see here the current will be leading the voltage by a 5/2. So that is the part we are mentioning it here. So here voltage lags current by pi/2, the same 90 degrees I am taking into account, the same 90 degrees. So you guys for the same 70.7% I must be careful with. So for 70.7% I am drawing it for voltage and current. Next for current, for voltage I draw an phasor. So it's making an angle omega t, then angle omega t. So here angular velocity is omega. So it is, the curve is, the current is leading the voltage. So you will be getting it on the other side. So when you're drawing it, please be careful. It should be drawn only at 90 degrees. So please be careful, especially when you're drawing it. So this is the phasor diagram. Thank you.